Welcome to Khetztutorials, and in this video I'll be covering rules of differentiation. In the previous video I talked about finding the derivative or differentiation using first principles. Now this is a quicker method of computing your derivatives, and it basically revolves around finding the behavior of your variables when you differentiate. And I'll just go right into the rules. I won't cover all the rules because only a limited number of them are actually part of the grade 12 syllabus. But yeah, so let's do what we're here for. Starting with rule 1, which is usually called the derivative of a constant, or we can just write it in short and just say constant. So how do we deal with constants? And by constant we basically mean real numbers. So let's talk about real numbers. A real number, which would be any value, basically any value you can think of: 165/4, -1, 0, 12, 1000, -1000, whatever the case may be. As long as it's a number, we basically refer to that thing as a real number or a constant. So let's say we have f of x equals to a real number. We can call it k, and this k is just a holder for just about any constant, right? So any number, any real value that you can think of. Now if you have this real value, the derivative of that would be, so f prime of x would be 0. So this is what the first rule basically says. If you have a constant, its derivative is just 0. And after talking about rule 2, we'll come back to this very thing and see how all of that actually works out. So rule 2 would be the power rule. So let's say rule 2 and let's call it power rule. Now using the power rule, we have this. So let's say we have a function and it has a variable x or a series of x values. Doesn't really matter, but let's only focus on just having one x value. Doesn't matter what the power is, so let's call the power n, because n can take on any value. Now if you have a function like this and you wish to differentiate it, then the derivative would basically be found by taking this power down here. So you take the power down, so you take the power all the way down there, then keep your variable but alter the exponent again by subtracting 1. So this is what you do if you had a function. It can be a function of any variable. Please keep note that, or take note that, if you have a function, it can be a function of just about any variable, right? Doesn't necessarily have to be a function of x. It can be a function of z. It can be a function of just about any variable. So when you're using your notation, and I will talk about notation a bit later, when you're using your notation, make sure that your notation is in keeping with the variable type that you have. In this case, we're dealing with x, so it makes sense to have x over there because the function is solely defined by the variable x. But now with rule 2, the main thing was that we basically take the exponent, take it down there, multiply your function by the exponent, then subtract 1 from the exponent. Now coming back to the top rule, which is rule 1, which talks about constants. So x, or any variable to the power 0, is basically equals to 1. So having a constant, you can basically say that the constant is basically multiplied by 1. That is a valid thing to say, because anything multiplied by 1 is itself. Now we can replace that 1 with x to the 0 and have our function as follows. And this is just me proving how we got to this conclusion over here. Now if you have k, which is a constant, multiplied by x to the 0, and you want to apply the power rule, and this x to the 0 is basically just 1, now your derivative should be k, which is just a constant, and then you're going to multiply that with the power of your variable, which is 0. Then you are going to subtract 1 from the power and have -1. Now if you look at this, everything is basically now multiplied by 0, which means the result, or the derivative would therefore be 0. So this is a way to prove that rule 1 is actually correct if you want to prove it, but just take it as it is. You don't really have to prove it. Whenever you have a constant and you want to find the derivative of that constant, it's basically 0. So that is as far as I will go with regards to rules 1 and 2. Now an example of rule 2. So let's just do an example of rule 2. Let's say we have, what can I say? Let's say we have x squared, right? And you're asked to find the derivative of this. Then you basically say f prime of x is equal to take the exponent down. So take it down here and have it multiply the original exponent minus 1. And now your result should be 2x to the 1. You don't necessarily have to write the 1, but you can if you want. So that would be the result, and that this is the derivative of that original function using the power rule, right? So those are the first two rules. Let's go to the other ones, or the next one. So rule 3. In this rule, we're going to talk about the derivative of a function when it's multiplied by a constant. So taking the previous example, so if you have, let's first write it in its general form. So if you have a function of x multiplied by a constant, so this is your constant, and this would be your function of x, right? F of x, so function of x. Now, having a function of x being multiplied by a constant, then this is how you basically deal with that. So your derivative would then be that constant. So nothing happens to the constant because these two things are multiplying each other. So nothing actually happens to the constant. You just focus on finding the derivative of the function of x. And then after that, you're basically just going to multiply the two. And if this looks abstract to you, then let's do an example. So for example, in the previous question, we had x squared, or in the previous example that I did, I had x squared. Now, what if we multiply this x squared by, let's say, 4? Now, if you do that, according to this third rule, we're just going to take the 4, then focus on finding the derivative of this function which we're multiplying 4 by. So now you can put brackets and only focus on this point. So the 4 doesn't change. Nothing actually happens to the 4 when you're finding the derivative. And now we're just going to focus on this. And if you look at that, you can actually apply the power rule, which is rule 2. And once again, you're going to take the 2 down, Then you're going to have your x to the power of the original exponent minus 1. And your result should be this. So now this 4 and that 2 are going to multiply, and your result should be 8x, right? Because 2 minus 1 is just 1, and you can write it in this form, or you can explicitly write the 1, which is not common, but you can. You won't be marked wrong for that. So now those are the first 3 rules. Let's move on to the next one. And in the end, I'm just going to do examples which combine all of these rules, because in most cases, you have to apply more than just one rule in a particular question. So you have to know all of these rules because they'll be put together in a question or in a test situation or whatever the case may be. And now moving on to rule 4, and we can call it the sum rule. And it's called the sum rule because you might find that we have a function made up of the sum of 2 other functions. And now if you want to find the derivative of this, you can find the derivative of the individual functions and basically add them up. And once again, if this looks abstract to you, then let's do an example. So for example, let's say we have f of x equals 2 x squared plus 5x, right? Then your derivative would be the derivative of this added to the derivative of that. So you treat them separately, and you can actually have 2 taken down, and then x to the 2 minus 1. Then on this side, you can apply the same rule and say 5 and then have 1. So this is rule 3, which talks about a constant multiplying a function of x. So the 5 remains the same, and then you take the exponent of your variable, then multiply with x to the power, the original exponent, subtract 1. Now in this case, you'd see that this will be x to the 0, which is basically 1. And now our final result would be f prime of x equals to 2x, because this is 1, plus 5, because this is 1 once again. So 5 multiplied by 1 multiplied by 1 would be 5. So this is our result, and that is how you'd apply this rule that says if you have two functions of x added to each other, you treat them separately and just add the result. Now, if you have the same question, I just want to extend this example. If you have the same question or a similar question, with the only difference being that you don't have x over there, now you'd also include the constant rule that we talked about. Now, if you find the derivative of this, just take the 2 down, then say x to the original exponent, subtract 1. Then now over here, this is a constant. So you're going to apply the constant rule. The derivative of a constant is just 0. So your final result would then be 2x, right? So as you can see, I actually put a few rules together to solve this one problem. So that is what you always have to look out for, and that is what you always have to do in most cases. And now let's look at the last rule as far as the syllabus is concerned, and that is rule 5. That is the difference rule. It's basically the same with the addition rule or the sum rule, which I just did. Difference rule, you can call it that. And it basically says that if you have a function defined by this, which is basically subtracting two functions of x, then when you find the derivative of that, you basically do the same as you did with addition or the sum. So you treat them separately. And for example, if you have f of x, so e.g., if you have f of x equals to 3 over x, subtract x squared. So this is x down here. Now the first question is, how do you approach such a question? So here's my advice. So first, make sure that your functions which you want to differentiate are in the simplest form, right? Which basically means that they're expanded as much as you can. And make sure that your functions, from your functions, you can basically see the exponents, right? Because you might want to use the power rule in most cases. So for the first point, let's say, for example, you had brackets or you had x plus 2 squared. You basically have to expand this so that it's x squared plus something, something, something. Then you differentiate this final form, because you can't apply the power rule to this because part of this thing is not an exponent, or it's not a variable. That is what I meant to say. So even though there's an x in here, you can't apply the power rule to this whole bracket over there. So you have to expand it. That is what the first point is about. Now with the second point about exponents, let's talk about it by looking at this particular example. Now we have f of x equals to 3 over x. And now I want to transform this whole thing into this kind of form where I can see all my exponents. And how do I do that? So from algebra, we know that if you have an exponent below the line or as a denominator, whatever the value is, so for example, let's say we have 1 over x squared. It's the same as x to the minus 2, right? And whatever the exponent is, we just take it up and put a negative. Now in this case, the exponent is just 1, and we can take that up and put a negative over there. So we have this in front of us, right? And this just stays the same because we can clearly see the exponent. So you want to get a form where you can clearly see your exponents, and you want to expand any brackets that you might have. And finally, we can now find the derivative. In doing so, we just basically take that exponent, which is minus 1, and we have a constant in front of a function of x, so we just keep the constant as it is. And now you're going to take your x, then the original exponent, then subtract 1, nothing different, nothing new over here. And then you do the same with this one. And now we also adding the difference rule, which we're talking about currently. And you have your 2 taken down. then you have your x, and then the original exponent subtract 1. So these are all the steps that you have to follow to get the answer for this one, and that is how you basically do it. And now all that's left is just to multiply what you have. That would be minus 3, and over here you have x to the minus 2, because minus 1 is minus 2. Then over here you have negative 2, x, and then 2 minus 1 is just 1, so you can just leave it as x over there. And you can leave your answer like this, or you can transform it to this form, just basically taking this below the line, and that's you basically using algebra or basic algebra. And this would then be your final answer. So that came from transforming the original question to this form, and then applying the power rule over there and there, then applying the constant rule, which is just that thing over there, just taking a constant as it is, and then focusing on finding the derivative of this, right? So it's a combination of some of the rules, and that is how you basically deal with them. You have negative 3x to the minus 2, take that below, and on this side we've done this x squared one quite a number of times now. Just take the 2 down, subtract 1 from the exponent, and you have your final answer over there. And that is where you basically stop, or that is how you'd find your answer. Now I'm just going to go through a few more examples just so we make all of this concrete. And before I move on to that, I want to talk about notation. So we have a few forms of notation, but the basic principle is that if you have a function of some variable, then your derivative should be with respect to that same variable. So if you want to find the derivative, then you basically use the same variable. So for example, if you have a function of z, the derivative should also be with respect to z. If you have a function of x, which is usually the case, your derivative should be with respect to x. Now this is the first notation. So the top would be the original function, and then here you basically have your derivative, right? And now moving on to the second type of notation, if you have d something, so variable 1 divided by d variable 2. Now variable 1 would be the variable which is affected by, or which is influenced by variable 2. And this is what I mean by that. Now, if you have y equals to 2x plus 1, then you'd see that a change in this x basically affects y. So y is affected by variable x. Now, if you want to use this kind of notation, then your derivative would be the affected variable, d of the affected variable, divided by d of the variable that actually affects the top variable. So you can look at this as some sort of subject, and you can look at this as being the influence. You can, not sure about these terms, but in I guess in English form you can talk about it in that sense. And yeah, this would be your notation. And once again, if you have something like z equals to 2k plus 1, you have to follow the same rule, which says that you basically use the variables that you currently have in front of you, and not just any random variables. In this case, if you wanted to find the derivative of this, you'd use the exact variables that you have, and your answer would just be, so looking at this, using the addition rule, using the constant rule, and looking at what we have, you have this, so just be 2 multiplied by 1 multiplied by k, 1 subtract 1, and this is a constant. The derivative of that would be 0, and your final result would just be, this is k to the 0, which is just 1, your result would just be 2. So I was just showing you the notation, or how you basically use this type of notation. Another type of notation, the third one, would be, let's see, would be this one. So dx, and let's say you have some sort of function in here, then you'd go ahead and find your derivative. So if you ever given a question like this, You don't specifically have to transform it into anything. All that you have to do is to find the derivative or to derive this thing, and your answer would just be 5. It stays as it is. Take the 2 down, and then x to the 2 minus 1. And then this is a constant, just be 0. And you'd have 10x as your answer. So this basically tells you that you just have to find the derivative of this thing. And the main variable is the variable which is over here. So if you have something which is like this, then you'll be dealing with z and so on. Now moving on to the last form of notation that I want to talk about, which is quite similar to this one. So you can either write it as this capital, or you can either write it as this. Now, the main reason why there isn't any variable at the top is because there is no subject relationship. There is no y is equals to. So we are dealing with the function itself directly. That is why you basically don't have any other variable at the top like you usually did. So we are saying we are dealing with this function exactly. It's not y equals to something or z or whatever other variable equals to this function. We just want to differentiate this exact function, and you basically do the same thing as you did over there. So these are similar notations, just that this one's basically a simplified or compact form of this notation. So that is all that I have to say about notation. I have also talked about notation in the previous video quite a bit. And let's move on to examples. So I basically covered a lot that I wanted to talk about in terms of examples as I was going through the rules, but let me just cover, let me cover three examples. A lot. I think 3 are a bit too much. So let me cover 2 examples. Let me cover 2 more examples because I've covered most of the stuff that I wanted to talk about when I was talking about the rules. And now let's say we have y equals to square root of x plus x squared, and you're asked to find dy dx. So how would you go about this? So the first thing would be to see if it's in the simplest form, and it indeed is in the simplest form, but we can't exactly see all the exponents to work with. So how would you do that? So if you have an n root, where n being some value over there, it can be 3, it can be whatever value. Now if it's not written, then it's basically square root, right? You basically know that. So now that there isn't any value written here, we know that this is a square root. Now how do we show the square root when we are talking about exponents? It's basically some exponent or some value to the power half. And this is how you take the exponents out of your equation. So this is basically the same as that. It's exactly the same. So now we just transformed it into this form so that we can see all the exponents and actually work with those exponents. Now finding dy over dx, we are now ready to do that. We're just going to take the exponent down, then say x to the half, subtract 1, nothing changes, it's just the power rule. Then the addition rule, you just add the derivative of the other function of x that you have, and you just take 2 down and say x to the 2 minus 1. Then you just continue like that. You basically have a half, then x to the minus a half, because a half minus 1 is negative a half. Then over here you just have 2 multiplied by 2 minus 1 is just 1, so 2 multiplied by x. And down here you're just going to continue to simplify. You can leave it like this if you want, but once again you can just use algebra to see that this x to the minus a half is basically the same as writing your answer as 1 over 2. The 1 over 2 is just that thing over there, and this would be that. So it's square root of x, but it has a negative sign, which means it has to go below the line, and this would be your final answer. So your answer should look something like this. And that is how you basically apply the things that we talked about to get to this point. Let me see what other question I can think of. So here's a bit of a, okay, let me make this point so I don't have to do the whole example. Let's say you had some sort of equation like this, and you're asked to find dy over dx. Now, if you look at this, it's not exactly in the form y equals to something. So you basically have to move stuff around and see how you can get your equation to this point. Then that is when you can start considering your derivative, right? So in this case, you just basically take this down and say, for example, 2y equals to x minus 4x squared. Then divide both sides by 2. You'd finally have y equals to a half multiplied by x and that. And then that half will basically multiply everything. And this is what you'd have. That cancels. And you now have y equals to x over 2 subtract 2x squared. And now I guess this can be your exercise or whatever you want to call it to basically find your derivative, and the answer which you expect to get is this. So you can do it by yourself and see if you actually get this answer. If you want to write it in descending powers of x, you can write it in this form. So now from the original part, which is this, you basically transform it into this form where you can exactly see that y is equals to something. Then after that, you can basically find your derivative, and the answer that you do expect is something like this. Right? So I won't go through how you actually get to that point. I can leave that as an exercise for you. But yeah, that is basically how you'd do that. And I just wanted to talk about rearranging the formula in that particular example. So I won't necessarily do that example. One example that I do want to talk about, but in passing, let's say we are asked to find ds dt given s equals to ut plus a half at squared. Now, it's important that you check the variables that you're dealing with. We're only dealing with s as the subject, as I previously mentioned, and t as the influence of s, right? So in this case, let's see, we have s over there, we have t over there, we have t over there. But the question now is, what about the other variables? There is no mention of the other variables, and there is no other equation to write these variables in terms of the variables that we're interested in, which are s and t. So if you ever have some other equations which allow you to write the existing variables in terms of s and t, then that is what you have to do. You have to write u and a in terms of s and t. But in this case, we don't necessarily have any other equation to write the u and the a in terms of s and t. So what do you do, or how do you deal with the u and a? So you basically just only focus on t. And now focusing on t would mean that you treat any other variable as a constant, just as a number, right? So dealing with this, you just say u, it's just a constant. Just have it like that and just have your 1. Then say t to the 1 minus 1. Then a half is a constant. A is also a constant in this case. Then you're going to have 2 taken down because we're dealing with t. Then 2 to the minus 1. Right? Then ds over dt will be equals to u. Then this is t to the 0, which is just 1. Then you have a. That can cancel out. Then you have a. Then this is just t. The final answer is u plus at. So the u is still there, the a is still there, because we treat these as constants because our main or subject variables are s and t. So I've talked about a lot now, and I think this video is quite long, but I hope you got something of value in the video. And if you do like this video, please give it a thumbs up. And if you haven't subscribed, please subscribe. If you have any comments, any questions, or anything, just let me know in the comments, or check the description for my email if you want to book like a private session where we talk about specific questions, or we have a Q&A, or you just want me to be your tutor or anything. You can also let me know via email. And that is all from me in this video. I'll see you in the next video.